Okay, we're going to do some examples now, and I'm going to take the time to show you step-by-step graphing, so dissecting what all the different transformations are doing and in what order. So we're going to graph ultimately y equals -2 times the absolute value of x minus 1 plus 3. But I'm going to do it one step at a time, starting with y equals the absolute value of x, and we would call that the parent function. So we know we have the one line that is y equals x, and then the other that is y equals the opposite of x, coming together in a V shape. And the point there at 0, 0, we can call that the vertex. Okay, the next transformation, or the first transformation I would do, is I would multiply it by 2. So we have y equals 2 times the absolute value of x. So remember, that's a vertical stretch. It's going to be 2 times taller. So let's take some of the points and double their y coordinates. 0, 0 is still 0, 0, but 1, 1 is now 1, 2. 2, 2 is now 2, 4. 4, 4 is now 4, 8. And then same thing on the other side. Okay. Oops, I think I missed a little bit. Let me do that side again. There we go. Okay, we should see symmetry across the y-axis. The next step I would do is the negative, so we have y equals the opposite, or -2, times the absolute value of x, and that's going to reflect the whole thing across the x-axis. So we still have 0, 0, but now we have 1, -2, 2, -4, 4, -8, and so on. Same idea on the other side. Okay, then the next transformation I would do is the -1. Now, for some problems, you could do the steps in different orders. Like you could do the -1 first, and then the ×2 and the negative, or the negative and then the 2. But you have to be kind of careful, because if you have reflections and shifts, sometimes you can get messed up if you don't do them in a particular order. And you can always take a point at the end, plug in the point into your equation, and see if it works to know if you graphed it in the right order. So the -1, so we're going to have y equals -2 times the absolute value of x minus 1. And remember, what that's going to do is shift the whole graph to the right one. So I'm looking at the graph that I just drew, and instead of 0, 0, we have 1, 0. And then we're going to shift the whole thing over. Right 1 unit. Okay, and then finally we have +3, so that's going to shift the whole graph up 3. So the vertex is not going to be at 1, 0, it's going to be at 1, 3. Shift everything up 3. Okay, now you might be wondering, why I don't just talk about slope? Like for the 2, why don't I just say it has a slope of 2 or a slope of -2? And that's because I want to generalize these ideas of transformations beyond just lines. So if we have curves or other kinds of graphs, then we won't necessarily talk about the slope. Okay, let's move on. So this time I decided, let's apply transformations to something curvy, like the x squared function. So we're going to graph y equals -3 times x plus 2 quantity squared, starting with y equals x squared. That would be the parent function. And I suspect you've probably had some experience graphing this before. It's a parabola, which is a U-shaped curve. It goes through 0, 0. 1 squared is 1, 2 squared is 4, 3 squared is 9, -1 squared is 1, -2 squared is 4, -3 squared is 9. So here is our parent function. Make sure it looks like a curve and not straight and pointy. And that point there at 0, 0 is called the vertex. So the next thing I would do is multiply by 3. You could do the +2 first if you wanted to. You could do the negative first if you wanted to. For this particular one, it's not going to make a difference. So it's going to be 3 times taller, so triple every y coordinate. 0, 0. Instead of 1, 1, you have 1, 3. Instead of 2, 4, you have 2, 12. Same thing on the other side, negative 1, 3, negative 2, 12. So 3 times as tall, vertical stretch by a factor of 3. And now for the negative, that's going to reflect it across the x-axis. So still 0, 0, but we have 1, negative 3, negative 1, negative 3, 2, negative 12, negative 2, negative 12. So there's a vertical stretch as well as a shift, excuse me, a vertical stretch as well as a reflection. And then finally, I'm going to put in there the plus 2 inside the squaring. Remember, if it's inside the function, it's a horizontal shift. And if it's x plus 2, it's going to be left 2, not right 2. So let's take what we just graphed and shift it left 2. Okay, there we go. All right, I'm going to skip number 3 if that's okay. And then what I want to show you with this one, this will be our new number 3, is that we don't even need to know the function. We don't have to have a particular equation. This one I'm just calling y equals f of x. And I've drawn a little graph. It's a function. It passes the vertical line test. It's made up of a segment of one line and a segment of another line. So what we're going to do is transform it until we get y equals 2 times f of x minus 1. So for the next step, let's draw y equals 2 times f of x. So that's a vertical stretch. It's going to be twice as tall. So we multiply all the y coordinates by 2. So the point that was at negative 2, 0 is still at negative 2, 0. The point that was at 0, 4 is now at 0, 8. The point that was at 5, 4 is now at 5, 8. And we can just connect to get all the points in between. And then we have to subtract 1 from what we just did, which is going to shift the whole thing down 1. So the point that was at negative 2, 0 is now at negative 2, negative 1. And the point that was at 0, 8 is now at 0, 7. And the point that was at 5, 8 is now at 5, 7. Okay. So here is your assignment. And I did throw in an even numbered problem. I do like this problem. And so because you don't have the answers to the evens, I wrote it here. Sorry, it's kind of rough to have to see it before you even see the problem, but just forget about that until the time comes when you need to know. Thanks. I know this is a long lesson, and I appreciate your attention today.